pure substance. If they're a mixture, then you're talking about things that are physically combined, so they can be separated physically. They might look uniform, that makes them homogeneous, or they might look layered, parts, pieces, different, sort of like you can tell that there's parts in them. That's the heterogeneous. Okay, so just remember, homo means the same, hetero means different. So it's just a way of like trying to make sure like that base. Now, if it's a pure substance, though, then that means that that matter is made up of only one substance. So you can take and split it and split it and split it, and you can't separate it physically into different things. The simplest of the pure substances are the elements. So the elements are on the periodic table. So if you see the name on the periodic table out of the 30 that you've got to learn, then you know that that's an element. It's a compound if it's more than one element chemically combined. So that's different than things just mixed together. Chemically combined means that, in like water, H2O, the hydrogen and the oxygen are chemically combined, and I can't physically separate them. The only way I could separate them is through chemical separation, okay? So if you're going like kind of the trick, if it's something on the periodic table, it's a pure substance and an element, okay? If it gives you a formula, then you know that it's going to be a compound. So it's a pure substance and a compound. So then we kind of started going through some of them as examples. So sometimes you need to have a little more like details because they might look one way or another depending on the conditions of the sample, especially if you're talking about like a homogeneous mixture. So this one, like unstirred paint. So if you've ever bought paint, and it sits in the closet or wherever you happen to keep it for a while, and then you open it, what do you see? There's layers, right? So it's got a clear liquid on top, and then you can see the colored paints underneath. So you got to take a stick and you start stirring it, okay? Now, if you buy it from Lowe's and they shake it, it's not going to look like that. When you take it home, you take the lid off, it's all uniform, right? So if it's shaken, then that means that those layers have all been mixed, and they'll look uniform for a while, but if it sits for a couple of weeks, you'll see that there's going to be like a liquid layer on the top that you have to mix in. So is that a mixture or a pure substance? It's a mixture. And if it's unstirred, it's going to look layered. That is hetero. Okay? So if you can tell that there's a liquid layer, a clear layer, a colored layer, if you can see pieces or parts, then that's going to be that heterogeneous mixture. So like the next one you might not know just from the name. But if I told you this, so if I said ammonia, NH3, what is that? So now you know this is a pure substance, and it's a compound. Because it's got a chemical formula in it, and you can see there's nitrogen and hydrogen. So you see more than one element listed as a formula. So the air. So again, you might need more information about it, or maybe you even have to like go, like, what is air composed of to figure it out. So air is about 79% nitrogen gas, about 21% oxygen. It does have very small amounts of stuff like carbon dioxide, water, argon, very small other gases that are mixed in. So this is a pure substance. If 79% is nitrogen, 21% is oxygen, it's a mixture, right? So there's more than one thing. These things are like floating around, nitrogen and oxygen, the biggest components of the air are floating around. So this is a gaseous mixture. But can you see layers, parts, pieces, or is it uniform? It's should be completely clear. Now on foggy mornings, you might be able to see water condensation, but under most conditions, it's going to be homogeneous. You won't be able to see it. You can't see any layers. Now the asphalt. So asphalt sort of like, think about the road, okay? So what do you know about that? Have you seen the big asphalt trucks? So what do you know is in asphalt? Rocks. What else? What makes it black? Does anybody know? Tar. In fact, if you've driven by when they're like laying it, tarring it, that smell, like that really strong tarry kind of smell. So there's rocks, tar, and sand. In fact, a lot of asphalt actually has glass ground up, which gives it a little bit of a reflective property. So you're like, why would you put glass in the ground? Like on something you're driving on. And it's not like sharp glass. It's glass that's kind of been tumbled, so it's more smooth, but it reflects light better. So that's why sometimes if you're driving, you'll notice like it's got some reflection to it, so it's not just black looking. So that's added in there too. So that makes asphalt a what? It's a mixture. But if you got up close, can you actually see parts and pieces? Can you see stuff in it? Yeah, you'd be able to see small rocks, small pebbles in it. So it's hetero because I can see variations in it. So on your test, I'll either give you examples just like the things that we've already talked about, or I would use things like cereal and milk. Okay, things like that are very familiar to you, things like that, that I would use as an example. So I'd give you the information about like what air is made up or what ammonia is actually composed of so that you would know the difference.
So how do I know like ammonia and air? Because I don't understand how ammonia is a pure substance and air is a mixture.
So ammonia is nothing but NH3. Just like if I had water, you would say water is a pure H. So if you see like even oxygen gas, so if I just said oxygen gas, then we're going to be talking about only oxygen, which is on the periodic table. So that's a pure substance. Whereas air is part this, part that. Okay. So one of the examples that they gave was brass, I think in your, in the textbook. So they said brass is a combination of copper and zinc. And the reason they do that is because copper will turn green. I don't know if you've ever seen like copper gets that greenish, it'll oxidize, but by adding the zinc, that slows it down. So that's why like a brass candlestick will stay that coppery color because it has the zinc added to it. But if I asked you about brass, I would give you that information that brass is composed of a combination of copper and zinc. So that means that brass is and then you would tell me it's a mixture. Because you can see that it's two or more things, and those are mixed together or physically combined. That's the big part. Now, there is a dynamic study module that is due Sunday night that's on what they call understanding matter, and it will give you a bunch of these kinds of questions. So it's going to go through and ask the difference between mixtures and pure substances, homogeneous, heterogeneous, give you examples and ask you to identify what they are. It's also going to go back over the states of matter, solids, liquids, and gases, and some of the characteristics that we've talked about. So that one is a good review for this, but we've actually gone through all of that material now. And I don't know why. It worked perfectly fine. Next. Okay, so all elements are pure substances if they're listed individually, and they're all on the periodic table. So you've got in that handout, the one that has the metric unit conversions, the ones that's got all of these, that 3-page handout that I gave you, that's the first page, and we'll probably talk about that next Wednesday. Balancing equations we're going to do tonight. But then you've also got this, okay? So this really matches the laminated one that you'll have on an exam. So it's a good one to use, and you can add like information to it as you go along. So the columns on the periodic table, they call those groups. And one reason that they organize the periodic table the way it is columns are similar. Okay, so a good example of that one is the very last column on the very far right. It's He, helium, Ne, neon, Ar is argon, Kr is krypton, Xe is xenon, radon. Those ones are named or were called the noble gases or the inert gases. And their characteristic is that they existed in nature and didn't form compounds. So they're very stable all by themselves. But that column was different than any other elements on the periodic table. Same thing if you go back one column, Fe, Cl, Br, and I, fluorine, chlorine, bromine, and iodine. So, for example, chlorine. What do you use chlorine for? okay? Put it in the pool, right? So it's a disinfectant. If you've ever been in or had a hot tub, you can get what they call bromine tablets because they do the exact same thing. They're in the same column. In fact, iodine, my leg, after I got my cast off, was all orange. Why? Because they do an iodine scrub as part of your surgical prep. Like scrubbing all that mess off for days, trying to get the orangey color out. But what it does is it's an antiseptic that helps to reduce the number of microbes on the surface of the skin, and that decreases surgical wound infections. So they like sit there and like they give you like a good 5-minute iodine scrub. I was out, I didn't even know. But I end up with this big orangey leg by the time they take the cast off. But look, they're all in the same column. Okay, so that's a good example of where these groups, these columns have similar characteristics. They react similarly, they behave similarly, and that allowed them to actually begin to organize the periodic table and even guess characteristics of unknown elements when they were first starting to discover elements. So if you look, copper, gold, and silver, which is Cu, Ag, and Au, those are all in the same column. And those are very commonly used to make jewelry, to twist, to fold, to shape. Copper, silver, gold, they're like the precious metals. In fact, copper has become extremely expensive just because of like with COVID and stuff, mining went down. And so the cost of copper like went through the roof. Gold and silver have been expensive for quite a while, but copper really got expensive. So those that are columns, really? See, I don't know why my little columns, these have very similar properties. And so you can think of like chlorine, bromine, iodine, even fluorine, but fluorine is really reactive. That's one of the reasons they don't really use fluorine as an antiseptic or a disinfectant. But you put chlorine in a pool, you can use bromine tablets in a hot tub, you can use iodine as a surgical scrub. So these are very good antimicrobial chemicals. The noble gases that are very unreactive, they're in the very far right. Over on the very far left, we have the alkali metals, and so that's like lithium, sodium, potassium. They react the same way. So if you take those and you put them in water, they react almost explosively with water. So ones in the columns are similar. But now what's different when you go across? They call those periods. So the period is going across. And if you look, what do you notice about the number above as you go from left to right? It goes up by 1. So if you go H to HE goes 1 to 2, then Li to Be goes 3 to 4. And if you keep going across, notice that number is called the atomic number. It increases by 1. So the number underneath is their mass. And so in general, the masses, the size of the atoms increase as you go left to right. So the size of the atoms that make up these elements increases as you go left to right. We're going to talk a little more about what those numbers mean in chapter 2. But there's one other big thing that you can use the periodic table for, and that is identification of the metals and the nonmetals. So if you look at your periodic table, the laminated one or the one that's on the paper one, okay? So if you look at one of those, you see that there is, and it's not on this one, which is why I don't use that one, but you see this zigzag line? So it's this sort of like bold line. It starts underneath B, which is boron, and it zigzags all the way down. Everything that is to the left is a metal. Everything that is to the right is a nonmetal. So you can say without a doubt, which do you have more of, metals or nonmetals? Lots more, okay? So there's more metals, there's fewer nonmetals. So when I look at them on this periodic table, which you always have up, I don't take it down or anything, all of the ones in black are solid. All of the ones in blue are liquid, and all the ones in red are gases. So that actually shows you the different states. The ones that are white and outlined, those are radioactive. They're very unstable. So pretty much as soon as they're made, they break down. So it's really hard to tell like characteristics about them. So that's why they're kind of whited out. But the black and the red and the blue. So you would say most metals are what? Solids, liquids, or gases? Solids, black. Okay, so look at your zigzag line from boron diagonally down towards astatine, which is At. So everything that's to the left, all but hydrogen, which is really not a metal. Hydrogen's kind of in a class all by itself. They put it over in that upper right corner. It doesn't really belong there, but size-wise it does. So it's kind of like the oddball. But if you look, everything else except what? These are solid. All except what is the liquid metal? Mercury. Right? So mercury is used like was used in the original blood pressure cuffs in a barometer. So they used to have a column of mercury as this silvery white liquid. Did you ever have mercury thermometers? Yeah. So we had mercury thermometers when we were kids, and like we would break them and then play with the mercury. So they're solid except mercury. Other characteristics of metals. So metals tend to be solid. Metals are really good at shaping. So they're shapeable, bendable. Some of them you can form a wire, like copper. You can actually, like, as it's cooling, you can begin to pull it. You can pull it into a wire. And then that wire has the ability to conduct electricity. Nonmetals, which are much fewer, and if you look at the zigzag line on your periodic table, you'll see most of those are what? NOFClHenearkRXe and Rn. They're all what? The majority of them are gases. There are some exceptions. Carbon is an exception. Silicon is an exception, phosphorus and sulfur. So there are some exceptions. There's only one liquid nonmetal, and that is you see the blue? Bromine is a liquid at room temperature. Okay, it's very close. It's like boiling point is very close to being room temperature, about 80 degrees. Bromine is a liquid. There are ones like carbon, nitrogen, sulfur, phosphorus, not nitrogen, carbon, sulfur, phosphorus is the other one I meant to put. And those ones are solids. Well, nonmetals, because most of them are gases, nonmetals really are not shapeable. In fact, the few that are solid are really brittle. So like if you take carbon, like a charcoal briquette, so like, you know, like a Kingsford charcoal briquette, if you take it and you hit it, it just like shatters. So you can't like take it and bend it. You can't roll it into a sheet or pull it into a wire. So all of these, they're either very brittle, not shapeable, or they exist as gases, and they don't conduct electricity. They're non-conductors. In fact, they're actually pretty good insulators. So they're good at like being used to try and like block electrical conduction. In fact, understanding about the nonmetals led to the development of computer chips. So in computer chips, they can take and put microscopically thin metal, thin wires put them really close together, but use non-metals to act as the insulator so that you can actually form like electrical currents with things that are like microscopically far apart. So they don't have to have like a big wire of copper covered with rubber, insulation. You don't have to have like what you think of when you like wire a house. They can take all of that and put it down into these little teeny tiny computer chips by understanding of using non-conductors along with those conductors. Now there is a couple of them. And you see the green. So boron, silicon, germanium, astatine, antimony, tellurium, polonium. These are what they call metalloids. Metalloids just have they're a little bit like a metal, a little bit like a non-metal. They tend to be more solid like metals are, but they're not as conductive as metals are. So they're kind of a both, and that's where that name came from. They used to call them like semi-metals, but now they call them metalloids. We don't really work with them very much. I mean, the only ones you need to know was just boron and silicon. Those are the only two for their names and elements. And so those are sort of the in-between ones. So these run right along the zigzag line. And they just kind of have properties of both. But that zigzag line really becomes important in chapter 3. We're going to talk about bonding, because whether something's a metal or a non-metal will determine the kind of chemical bonds that it can form. Okay, so you can see those in this one. Then I gave you the names of the elements, the ones that I want you to make sure that you know the names and the symbols for. So it's 1 through 20. And by 1 through 20, I mean the number above each of the letter symbols. Notice with the symbols, if there's only one, it's capitalized. But if there's two, the first letter is capitalized and the second letter is always lowercase. Right? So like chromium, so that way you don't mistake. Like CR, capital C, little r, tells you it's chromium and not carbon with some R. Seeing capital C, if I see this, I know that this is cobalt, capital C, little o. But if you wrote it like this would actually be carbon and oxygen. So that is why if there's a second letter, always make sure you do it in lowercase so that you don't get those ones mixed up. And if you see in a formula, you will always have the symbol and then the number after tells you how many of those elements you have in a molecule in one individual unit. So this one, there's 6 carbons, 12 hydrogens, and 6 oxygen. If you don't see a number, like what happens like with H2O, then that just means there's 1. So there's 2 hydrogens and 1 oxygen. So this one, you know that it's 1, but they don't put that in. The 1 through 20, the extra 10 that I gave you, chromium, iron, cobalt, copper, zinc, bromine, silver, gold, mercury, and iodine, the reason that I have those ones for you to learn are because we're going to talk about them again. So this is not like the only time that you're going to see their symbols. You'll see them again. So being familiar with those ones is really going to help. So in terms of the living organisms in the human body, there's about 27 different elements that are found in the body. They are typically combined with other atoms into compounds. Some of them are really big. Some of them can be really small. Some of them exist as an ion. Some of them exist as large molecules. They've split them into what they call the main group or the main elements. The main elements, they make up 96% of the elements in the body. And they're the ones that spell out carbon, hydrogen, oxygen, and nitrogen. So I just always remember this as CHM, which isn't a word, but it's sort of a mnemonic to remember. 96% of what is you is carbon, hydrogen, oxygen, and nitrogen. So the other 24 elements only make up a total of 4%. In fact, the minor elements make up 7 of those 24, and all together, those only make up 3.9%. And so this is sodium, Na, magnesium, Mg, potassium, which is K, calcium, Ca, chlorine, Cl, and this includes sulfur, S, and phosphorus, which is P. So those are the 7. So they call those the minor elements. So that means just 11 atoms on the periodic table make up 99.9% of you. It's not very many, like compared to the fact there's 118, and only 11 of them make up the majority of you. So the other ones, the other 16? The other 16, they call those the micronutrients, or I've always referred to them as the trace elements. Trace elements are found all together only 0.1%. So they're found in very small concentrations. And I always think of trace elements as being involved in very specific jobs. So things like iodine. So does anybody know there's only one gland in your body that uses iodine? Anybody know? One set of cells in one gland that needs iodine. This is required by your thyroid. So it's the only place. So if you ingest any iodine, that's where it goes. So your thyroid is this small gland. It's got like bilobed. It's got 2 little lumps connected. It's here, just like if you feel for your Adam's apple. It's like just below and to either side of your windpipe. But that's the only, if you ingest it, and typically you get iodine from any kind of seafood, any kind of shellfish, just because it's found in pretty good abundance in the ocean. So fish tend to have iodine. That's all you have to have. How about Fe? Fe is iron. And iron is, again, you don't just randomly find iron. In fact, free-floating iron would be toxic to cells. Instead, iron is sent where? What's it used to make? What cells have to have iron in order to be functional? So the liver can store iron, but the liver sends iron to your bone marrow so that you can make what? So you can make red blood cells. So low iron, the biggest issue with low iron is anemia, is you end up with low numbers of red blood cells. And that means, so your red blood cells, their job is to carry oxygen. And so if you don't have a lot of red blood cells, then your blood can't carry very much oxygen. So you get winded, you get tired. If you stand up really fast, you get kind of woozy. Oftentimes people are kind of pale looking if they're anemic. So like their gums will look pale, or they're just pale in complexion. So that's really the major job of iron. Now you also store some iron in your muscles. That's why your muscles are red in color. And that's all because of that iron as well. But the biggest thing really is for that iron to be able to make red blood cells. Some of these are ones that maybe, like those I think are really two good examples. They've got some others. Those are the ones that are shown in like purple. So like these two, zinc and selenium. Sometimes they put this in orange juice. Has anybody ever bought any orange juice that has added zinc and selenium? Both of these are known to help improve what function? Both of these can help improve immunity. These are known to stimulate your white blood cells. So if you've got a bad cold, they always tell you to drink orange juice. Well, make sure you get the orange juice with some zinc and selenium. Because you get the vitamin C, which is a good antioxidant, but you also get the added zinc and selenium, which may help your white blood cells respond faster. So we don't eat a lot of fluorine, but what do we use fluorine for? Toothpaste, yeah, because the fluorine will actually bind to the enamel in your teeth and help make it more resistant to break down or dissolve it by acids. So it helps to make your enamel stronger. So it's in the body, so it's there, but again, you don't have it in a whole lot of places. Pretty specific. So these aren't all of them. These are just some of them, the little trace elements. But it does actually, they do have the 7 marked that are the minor elements. They're in orange: sodium, potassium, calcium, magnesium, phosphorus, sulfur, and chlorine. And then you see CHM. You see the carbon, hydrogen, oxygen, and nitrogen. So we talked about the states of matter. We talked about the characteristics of matter that go on. We talked about how the shape and the volume is different between solids, liquids, and gases. How that vibrational activity or the kinetic energy is different between solids and liquids and gases. How the particles actually look. So we can take a solid and melt it to become a liquid, right? So you can take ice, put it out on the countertop, let it sit, and eventually got a puddle of water. So this, going from a solid to a liquid, or boiling water, going from a liquid to a gas, all of those are examples of what they call a physical change. Because a physical change is when you change what the substance looks like, but it's still the same substance, and I can change it back. Okay, so the identity is the same. So I can melt and take a solid into a liquid. But I can do the exact opposite, and I could freeze and change the liquid back into a solid, right? So the molecule doesn't actually change. I can change it back. So things like boiling, freezing, melting, all good examples of physical changes. But I could also like chop. So like when you make salad, right? So you make salad, you really just cut up all the vegetables so that they're easier to eat. But if you take a carrot and you chop it, it's still a carrot, right? So that's a physical change. So I just chopped it in smaller pieces. You take lettuce and you break it all up. It's still a physical change. It's still all the same stuff. I have not chemically changed it. I'm just making it a little easier to eat. So chopping things, breaking things, into pieces. Wait, go back. Into pieces, all good example of physical changes. And that's really the way to think about it. Think, okay, ultimately, have I changed it? Could I like take the pieces of the carrot and like put them back together and it would look the same? Could I make it look back the way it was before? If so, that's a chemical change. But what happens if you light charcoal? So you pile up your charcoal, you add a little bit of lighter fluid, and then you throw the match, and now you see flames. Over time, does the charcoal change in its appearance? Yeah, it gets kind of gray. So it goes from being black and it gets kind of gray, but you can feel heat being released from it. And if you don't like cover it up and you let it just keep going, eventually what will you start to notice about the size of the charcoal? It's going to get smaller, right? So you'll start to notice like the little charcoal pieces look like they're actually getting smaller. And eventually you'll be left with nothing but what? Ashes, like just this gray dust. Can you take it and pack it back together or warm it or cool it and convert it back to charcoal? No. So I have made a change that I can't just change it back by heating, cooling, or pushing things back together. That's a chemical change. So a chemical change results in a change in the chemical identity of a substance. I've changed what it is. So things like, if you say things are burning, if there is heat released or absorbed, if the substance like disappears, I can't make it back. If you see like there's a smell that is sometimes given off, because oftentimes gases, you'll have like an odor, like even like chlorine. Okay, so like you open a bottle of bleach, so that smell that you smell. You might also see things like bubbles, the release of carbon dioxide from soda. That's a chemical reaction. So if you let it sit long enough, it stops bubbling. And if you taste it, what does it taste like? It's flat. Like it loses that carbonation. So that carbonation is actually a chemical reaction. And I can't just put the lid on and make it become bubbly again, right? Once it gets flat, that's it. It's flat. So those are things to look for where I've actually changed the composition of the substance. So when that happens, they call that a chemical reaction. So a chemical reaction is when there is a chemical change that a substance undergoes. So we can go even further with this and start to talk about, well, what does a chemical reaction look like? And so their example follows along with the charcoal. So charcoal in this one, charcoal is carbon. So this is, you can use like these little balls to kind of represent this. Or you could use their symbols to represent it. And so what happens when you light charcoal, you're lighting carbon, and by adding that initial flame, that allows the carbon to combine with oxygen. So oxygen gas, which is in the air, will combine with the carbon, and it will form carbon dioxide gas. And this is why the charcoal looks like it disappears, because it begins to form carbon dioxide, and carbon dioxide's a gas. So that is why the solid carbon just gets smaller and smaller and smaller, and eventually you're just left with the ash that's left behind. And really the ash is nothing but like the salts that was in the wood, the part of the wood that wouldn't burn anyways. That's really what ashes are. These are just metals that were in the wood. So we could also write it as a chemical formula. So in this, C plus O2 reacts to form CO2. Everything that's on the left is considered a reactant. I always think of it as being the starting material. This is what I started with. Everything that's on the other side is a product. This is my resulting material or what I end up with. And the arrow separates them. So when you see this little parentheses with an S, that is telling you the state that the substance is in. So that's a solid. After oxygen, you have a G, so that's a gas. If it was water was involved in this reaction, you might see H2O with an L, which just tells you it's a liquid. There might also be this. So like if you make a solution of salt, so if you take a cup of water and add a spoonful of salt, stir it up, it dissolves. They would say that that salt is dissolved in the water, and they use the term AQ, which is aqueous. So aqueous just means dissolved in water. So those are sort of some of the indications about state that you might see in a chemical reaction. And so like I said, this is kind of like the divider. The arrow separates what you start with and what you end up with. So you know when you burn charcoal, there's heat that's given off. So in this case, they put heat above the arrow to tell you that there's heat that's released. Sometimes you'll also see it written over here, which indicates like heat is a product. Heat comes off when you're burning the charcoal. The heat that's given off is what you use for grilling. So you might see it over on the product side.
Is there a preferred way, or does it matter?
So you'll just see both, and so that's why I just want you to recognize. I like to put it as a reactant or a product because I think it makes more sense. Because if you have there are some reactions where the sample will actually get cold because heat is actually a reactant. So heat is used in the reaction, so your sample might get cold. Like if you ever had a cold pack, so you like where they have like the little bubble inside, so it's like this, it sounds almost like salty crystals inside, and there's this little blister bubble pack, and you have to smack it and shake it, and then it gets really cold, okay? So the crystals, that's ammonium chloride, and inside is water. And when you hydrate that ammonium chloride, it absorbs heat, and that's why it gets cold. So in that example, heat would actually be on the reactant side because you would be using it, and that's why it would feel cold, like loss of heat would feel cold. So I like to put it on one side or the other, but if you see it like that, that's always going to mean that heat's coming out, that you're going to get heat with it. I just wish they'd be a little more consistent. But that's just me. I didn't write the book. Okay, so next, the rule is we have to make sure that the total number of atoms on both sides of a reaction are the same. So this leads us into the balancing equations. The law of conservation of mass says the number of each atom on both sides of the reaction have to be the same. Like we can't just make or lose any atoms in a reaction. So we're not going to change the formula, right? So if we have carbon plus oxygen reacts to form carbon dioxide, right? Whether we have the solids and the gases indicated in there. We have to have the total number of carbon on both sides the same, total number of oxygen on both sides the same. So we can do this and balance it by using what they call the coefficient. The coefficient would be the number of carbons or oxygens or carbon dioxides that I would have to either use or make in order to have those equal. So the steps that I do when I balance an equation is I list what the number of atoms per formula is first. So over on the reactant side, if I have C, that means I just have one carbon. So from the formula, if it's just C, that's one carbon. I have O2 though, which tells me that I have 2 oxygen. So from the formula, I have 2 oxygen. Then I got to do the product side too. So on the product side, I have CO2, which means that I have 1 carbon in the formula, and then O2 means 2 oxygen. So does everybody see where I got those? Okay, it's just the total number of atoms based on the formula. So then you can kind of compare. So I can compare carbons, I can compare oxygens. This one's super easy because what do you see? They're both what? Exactly the same. Okay, so they're exactly the same. So this means the carbon and the carbon, they're already balanced. The oxygen and the oxygen are already balanced. So that means I only need to use a 1. So this reads now 1 carbon plus 1 oxygen will form 1 carbon dioxide. So that's like if you were going to read this as a sentence, that's really what a chemical equation tells you. It tells you what the reactants are and what the products are. That's where the arrow comes in. It splits them, but you always have to make sure the total number of each is the same. So let's look at an example where that's not the case. And just a simple example would just be formation of water. So if we were going to make water, then we would have H2, hydrogen gas, the line in front, plus O2, oxygen gas. They would react to form H2O. So I have each one. I put a line in front of each of the formulas because that would be the coefficient that I might have to change if they're not already balanced. So now in this, if I draw the line, how many hydrogens on the left? From the formula, I have 2 hydrogens. How many oxygen on the left? 2. Because it's O2, so 2 hydrogen in H2, 2 oxygen in O2. But now over on the right side, how many hydrogen? And how many oxygen? Only 1. So do you see that they're not the same in this one? So I can't just have a 1 and 1 and 1. I'm always going to increase. You're going to pick the atoms that are not the same, so hydrogens are okay, but oxygens are not balanced. So I'm going to pick the side where I have a lower number. What can I multiply by that oxygen by to have it balance on the reactant side? So what do I have to multiply this by to have it equal to the reactant side? Multiply it by 2. So if I multiply this by 2, do you see that will give you 2 oxygens? And I always write OXY because otherwise it looks like a 0. So it's just a way of me keeping up with an oxygen versus a 20. So do you see that? So that 2 goes up here. Whatever I multiply it by goes on the line in front of the molecule. But do you notice that that means not only am I multiplying the oxygen by 2, I've also got to multiply the H by 2. So this, the number 2, whatever I multiply times 2, the entire molecule gets multiplied times 2. So now how many hydrogens do I have? 4. So my oxygens, you see that my oxygens are balanced, 2 and 2. But now my hydrogens are not. And that's okay. All that I have to do to fix it is I just have to change those hydrogens. Which side will I need to change in this one? Oh, no, I don't want subtitles. Look, no, I don't want subtitles. Now it's trying to stop subtitles. I didn't even know I could do that. It's always something. Ink. I'm just trying to change. I think it's easier to see it if I change the colors as I go. Okay, so the 2 that's in purple that I multiplied by the oxygen, I've got to double the hydrogen as well. So now when I go back, I have 4 hydrogen on the right and only 2 hydrogen on the left. So what do I have to multiply this hydrogen by to have 4? 2 more. So that's going to give me 4 hydrogen, and this 2 goes here. I don't have to put a 2 in front of the oxygen because those are 2 separate molecules on the left-hand side. So now what do you see? Are they the same, or are they balanced on right and left, or are they still different? They're balanced now. Okay, so I have a total of 4 hydrogen on the left, 4 hydrogen on the right, 2 oxygen on the left, 2 oxygen on the right. So the one that's blank, you can either leave it blank. I'm okay with that. You can either leave it blank or you could just put a 1. Okay, if you get done, you don't have to have a different number in every line. So if you get done and notice, like, I didn't have to do anything to the oxygen on the left, I didn't have to multiply it times anything. So that means all I would have to have is 1 of those. Now, if I was going to read this chemical equation, I would say 2 hydrogen plus 1 oxygen reacts to form 2 water molecules. So that ratio tells me how they combine. So So another way to think about it is like, if you've ever done any cooking, you don't use equal amounts of stuff. Like if you make a cake, right? So you use like a cup of oil, 2 eggs, half a cup of water. So you don't use the exact same amounts. The same thing here. You don't necessarily use the exact same amount of reactants and products. You're doing that to make sure that the total number of atoms of each type on both sides are the same. So look at these. See if you can figure this one out. So Mg plus N2 makes Mg3N2. And follow the steps, so I kind of listed how I do it. So 1, I list the number of each atom according to the formula. I draw a line. Mg is just 1 Mg. N2 is 2 nitrogens. I do that on the reactant side, then I do it on the product side. Okay, so did everybody get this far? So Mg plus N2 makes Mg3N2. So on the left side, 1 magnesium, 2 nitrogens. On the right side, 3 magnesium, 2 nitrogen. Everybody got that? Okay, so now when you look, which ones are not balanced already? The magnesium. So in order to balance them, what do I need to do? Okay, so I'm going to have to change which side? The left. So that means I'm going to have to multiply this times 3, give me 3 magnesium, so this 3 goes up here. Because magnesium and nitrogen are in separate, they're separate molecules on the left side, I don't have to multiply the nitrogen by 3 because they're separate. If I had to change the number on the right side, I would have to multiply both of them, okay? Because whatever number you put on that line, whatever's behind it, you have to multiply. So in this one, I've only got to multiply the magnesium by 3, not the nitrogen on the left. So now what? Do I have to do anything else? No. So that one's balanced. So that means you can just put a 1 and a 1, or you could leave it blank. If you just had that 1, 3, it would be fine. I know some students that never put the 1, and I know other students that always put the 1. I put the 1 because it makes me check myself. Like that's just a way that I can go back and be sure. What does the parentheses mean? So this is the next thing that always like people are like, I don't know how to do this. What's parentheses? Think about math. So when you see parentheses, let's do this one. So Al2 parentheses CO3 parentheses 3. How many aluminum? 2. So I have 2 aluminum. How many carbon? Nope. Nope. So remember, so it's CO3. So how many carbon is that? Inside is 1. So I have to multiply it times 3. So how many carbon? Just 3 carbon. Now how many oxygen? That one's 9. Right? So remember, whenever you have in math, if you have something in parentheses and a number outside, everything inside gets multiplied by the number that's outside. So in CO3, remember that if you don't see a number, that means it's just a 1, right? So CO3 means there's only 1 carbon times 3. So I have 3 carbons and I have 9 oxygen. So Al2O3, what is that? 2 aluminum and 3 oxygen. And then CO2. And 2 oxygen. So in this one, do you see that I have aluminum on one side each, carbon on one side each? But do you see the oxygen? On the oxygen's only in one molecule on the left, but it's in two molecules on the right side. So because of that, I want you to balance oxygen last. So the step 2, it says find an element that is located in only one reactant and one product. Balance that one. Leave the oxygens till last, and you will find that most of the time they will balance themselves. If you balance the simple ones, the more complicated ones will balance themselves. So do I have to balance the aluminum? No. So aluminum's already balanced, so that one's 2 and 2. What about carbon? Okay, so I have 3 carbon on the left, 1 carbon on the right. Which side do I change? The right. You're always going to change the lower number. What do I have to multiply by to make it balance? So I have to do times 3 to make 3 carbon. But that means this 3 goes on top, right? So what else do I multiply by 3? The 2 oxygens. Not all the oxygens, just the 2 oxygens. So that means this one gets multiplied by 3. That's going to give me 6 oxygen. So I'm only multiplying the oxygen that's part of the CO2. So go back. I always go back and check. Aluminum still 2 and 2. Now carbon is 3 and 3. Now the total number of oxygen on the left is the total number of oxygen on the right. And, so you have the total number of oxygens. See how I have 3 oxygens in Al2O3 and 6 oxygens now in 3 CO2s? So if I add those together, do you see that this is 9 oxygen? So now those are balanced. So that's what I mean by balance the simple ones first. So this would get a 1 and that would get a 1. Okay, so I've got a couple, so I want you to practice a few, and then we'll go over them just to make sure. All right, so in this one, first thing to do is draw a line through the arrow, right? Because that's going to help you split reactants and products. Remember what you start with and what you end with. Second thing, you list the number of atoms on each side. So H2O has 2 hydrogens and 1 oxygen. And then Na has sodium, okay? So just from the formula on the left, I've got 2 hydrogens, 1 oxygen, 1 sodium. Then if I go over to the product side, H2 gives me 2 hydrogens. NaOH is 1 sodium, 1 oxygen, and another hydrogen. So what you may want to do, so notice the hydrogen is in 2 places over on the right side. You might want to connect them. Just so that you go back and you remember that total number of hydrogen have to balance. But always check the simple ones first. So I would say sodium is simple because it's only in one part. It's a single atom one sodium on either side. But they're already balanced. Then I would check oxygen. Well, oxygen is also balanced, 1 and 1. So that means I've got to balance the hydrogens. So no matter what I do, on the reactant side, I'm always going to have 2 hydrogens. So that means that I need to make my hydrogens on the product side an even number. Okay, so that I can balance, I need to make sure that my hydrogens on the product side are an even number. So which of those hydrogens would I want to change to make it an even number? So the H2 or the NaOH? Change the NaOH, because the NaOH is 1 hydrogen. If I can make that one 2, then I can balance the even numbers. I can never balance the odd and an even, but if I can make 1 an even, so this is the one I got to change. So to make NaOH have 2 hydrogens, an even number, I'm going to multiply it times 2. It's going to give me 2 hydrogens, but remember that's going to put that 2 up there. If I multiply the hydrogen of NaOH times 2, I have to multiply the sodium and the oxygen because they're all part of one molecule. So now I have 2 NAs and I have 2 oxygens. And a total of how many hydrogen? 4. So does everybody see that? I have 2 hydrogen here, and now I have 2 hydrogen here, so that's 4. So when you look at that, you're like, well, I just unbalanced everything. Okay? That's okay. Because now I can go back, and when I balance, they'll be all right. So how do I balance the sodium now? Do I balance on the right or the left? The left. So I have 2 sodium. So in order to make this 2 sodium, what do I have to do? Times 2. And since Na is all by itself, I'm only changing just the sodium. So that 2 goes up here. So I balanced 1. Now I'm going to balance the oxygen because remember I said always balance the simple ones first. So go back and balance the sodium, then go back and balance the oxygen. So I have 2 oxygens here. So how do I make this have 2? Times 2. This is going to give me 2 oxygen. But then I got to put this number up here. Since I multiplied my oxygen by 2, I've got to put a 2 up on the line. So that means that hydrogen ends up times 2, and that's going to give me 4 hydrogen. So what did I do there? 2 sodium, 2 sodium, 2 oxygen, 2 oxygen. How many hydrogen? On both sides, yeah? So when you count them, 2 hydrogens here and another 2 hydrogens here. So that makes those balanced. So the one that I didn't have to change, that 1 hydrogen just stays a 1. If you see something in parentheses, like I just gave you an example, so A2B3 parentheses 2, remember that means that everything inside gets multiplied by what's outside. So A2 becomes A4, B3 becomes B6. Okay, so if you have to break when you're going to do balancing and you see parentheses, just break those back down. So we're going to put a line. How many aluminum in Al2SO43? 2 aluminum. How many sulfur? 3 sulfur. How many oxygen? So 4 times 3 is 12. And then we still got H2O on that side. So H2O, how many hydrogens? 2 H's and 1 more oxygen. So link those together. Link the oxygens together because they're on the same side. So you remember, do those last. Then go over to the other side. So how many aluminum? 1 aluminum. How many oxygen? Times 3, because see, it's OH with the parentheses 3. So that means I have 3 oxygen and I have 3 hydrogens. So that parentheses, everything inside is multiplied by what's outside. Now I got to do H2SO4. So how many hydrogen? And sulfur? 1. And then oxygen again. 4. So do you notice on this side, I have oxygens and I have hydrogens. Okay, so I would definitely leave the oxygens to last. I would balance aluminum is found in one place on either side. Then I would balance sulfur because they're in one place on either side. Then I would balance hydrogens because hydrogens are in one place on one side, 2 places on the other side. I would balance oxygen last. Because do you see that oxygen's like in every single molecule? It's on both sides. So let's balance aluminum first. So what do we need to do? So the smaller number over on the right side means I got to multiply this times 2 Gives me 2 aluminum. But now that 2 goes where? Up on the line. So that means now I got to multiply everything in that molecule. So not only the aluminum, I've got to multiply it times this oxygen, giving me 6 oxygen, and by this hydrogen, giving me 6 hydrogen. So everybody sees where you do that. Okay? Whatever number goes in front, all the atoms in that molecule get multiplied by that coefficient. So my aluminums are balanced. What's the one I want to balance next? Sulfur, right? So you see sulfur is only in one place on either side. So what do I want? Which side do I change? The right. So what do I have to multiply the sulfur by? 3. That means a 3 goes up here. Whatever I multiply by to balance, it's got to go up on that coefficient. And that means now I've got to multiply the hydrogen times 3, giving me 6 hydrogens here, and the oxygens by 3, giving me 12 oxygen. So I did the aluminum, I did the sulfur. Now I've got to check the hydrogens. So on the left side, how many hydrogen? 2. On the right side, how many hydrogen total? 12. Does everybody see that? Does everybody see this? I have 12 hydrogens total, 6, so 2 hydrogen on the reactant side. So that means I've got to increase the smaller number. What do I multiply it by to make 12? So I'm going to have to say times 6 to give me 12 hydrogens. That's going to balance the total number of hydrogens. So what goes on the line? 6 goes up here. Whatever you multiply by has to go on the coefficient up on the line. But that means I'm not only multiplying hydrogen by 6, I've also got to multiply the oxygen because it's H2O. So I've got to multiply this oxygen by 6. That's going to give me 6 oxygen. Now you go back. Are the aluminum still balanced? Do you see 2 and 2 on both sides? Sulfur, are they still balanced? Yep. Okay, hydrogens are now 12 and 12. So now you have to balance the oxygen. So how many oxygen total on the left? How many oxygens total? I have 18. Okay, so now let's go find them on the right. How many oxygen total on the right? 18. So see what I mean? If you balance the simpler, balance the aluminum, balance the sulfur, balance the one that are found less and fewer molecules on either side, oftentimes the more complicated looking oxygens, it's almost always the oxygen and hydrogens that cause trouble, those ones will just like balance themselves. They'll come out balanced. So what goes in this line? Just a 1. I didn't have to change that. The aluminum sulfate didn't get changed at all, so it just means it's just a 1. So that one's a good one to try, like practicing with those parentheses. And also when you see the multiple stuff, when you have more oxygen in more than one molecule on either side, always choose to balance the simplest ones first. Try the last one. And I always just started off like doing this, like doing the line. Draw the line, and that helps me to remember that everything on one side balances the other side. And sometimes when you balance one, it messes up another one, but that's okay. Just go back and balance it again. So which one did you choose to balance first? You see they're all only 1. There's only 1 hydrogen on either side, 1 chlorine on either side, 1 oxygen on either side. So you can pick. Did you try to do one first? Okay, so which did you balance first? Hydrogen, chlorine, or oxygen? So you balance the hydrogen. So on the left side, I have 2. On the right side, I only have 1. Okay, so I know that I'm going to have to change the right side. So over here, I want to make my hydrogens a 2. So I have to multiply it times 2. But that means this 2 goes on the line. So not only do I multiply the hydrogen, what else? I got to multiply the chlorine. And so when you look, do you see doing that, you fixed your chlorine? Do you see that the hydrogen and chlorine are both balanced? So you're like, all right, that looks good. So now I got to balance oxygen. So which side do I have to change? I got to change the left in this one. Okay, so I have 2 oxygens on the right, only 1 oxygen on the left. So in order to have 2 oxygens, what do I have to multiply it by? Times 2. It's going to give me 2 oxygens. The 2 goes up there. What I multiply by goes up on the top. But now what else do I have to multiply? Yes. So do you see, like, it was fine, and now it's not. That's okay. Don't be like, I did it wrong. No, you didn't. Sometimes you just have to fiddle with these numbers a little bit. Okay, so do you see, though, that when I fixed one, it messed up the other? Okay, keep going. So pick another one now. So now I need to balance either, I got to balance, everything is balanced now, but what? Just the hydrogen's not right. Do you see that? So I have 4 hydrogens on the left, only 2 hydrogens on the right. So what do I have to multiply that 2 by? 2 more. So I'm going to have to multiply it times 2, which means this goes times 2 to give me 4 hydrogens. But what else does that multiply it by? Right? So notice when I put that 2 in front of the HCl, that means this gets multiplied by 2 as well. So now I've got 4 Cls. And so now you're like, well, now I just messed up the chlorines. That's okay. Because now, when we finally get to the point of balancing the chlorines, 4 chlorines on the right side, 2 chlorines on the left, what do I multiply this by? 2. That's going to give me 4 chlorines. That 2 goes here, and it doesn't mess anything up. 4 chlorines on both sides, 4 hydrogens on both sides, 2 oxygens on both sides. I don't have to change this, so it can just stay a 1. And if you see that 2 times 2 because you had to go back and change the number, that's okay. All I do is just continue to add coefficients, but I know at the end this will be a 4 because 2 times 2 is 4. So just change it at the end. So you will see that sometimes. You will see like, okay, this is balanced, this one's not, I'll balance this one. Okay, now I messed that one up. So then I fix that, oh, now that messed this one up. So sometimes you have to go back and change your coefficients more than once. That's okay. At the end of the day, as long as I have the simplest whole number ratio. So I would read this and say 2 chlorine plus 2 water molecules react to form 4 HCl and 1 oxygen. So that's what those coefficients are telling me. They're telling me how many of each I would need in order for that reaction to occur. Okay, so not terrible. It's just really a practice thing. So what I want you to do is make sure between now and next Wednesday, because remember I don't see you Monday, between now and next Wednesday, practice this. Okay, and if you think like, I think I got it, there is in that handout that I gave you, the one with the periodic table, the page where the starting is the unit conversions that we're going to do next time. Make sure you bring that. The whole second page, front and back, is nothing but balancing equations. Okay, so there is upwards of, I think, about 40 equations to balance. Some of them are really simple. Some of them are a little complicated. So don't get super frustrated if there's 1 or 2 that you're like, I can't do it. That does happen sometimes. Okay, so that'll be all right. But here's ones to practice. And try and like start them like in the next day or 2 because we just did them. If you wait, you don't look at it again till Sunday, Monday, then a whole lot of life happened. And then things like kind of start getting a little like, remember again. You know, it's like, seems like it doesn't hold. Try and look at this in the next 48 hours because that will help what we've just talked about kind of come forward. And you're like, oh yeah, go back through. Okay? All right, so I hope you have a good MLK day on Monday. lots of things done.
Is there like an answer key or something in
There
where we
is.
can check out?
Yep, so I can show you that. So in Moodle, somewhere. Oh, you're not connected now?
Because this is just practice runs, right?
Yes, so you're not gonna turn that in. So you won't have to worry about turning it in. But in Moodle, if you go to 122, change them. There, it's gonna come back. It's coming back. So if you go to Chem 130, okay, and just so that you see, like I told you that I record and post stuff. So I did get the tutoring times. Those times are actually right now. So like mine are listed over on the right column over here underneath my face. That's my times. But then Ms. Williams, there's her times for the semester. And then Kendall Proctor, she's the student tutor. There's her times as well. So that's there in case you ever want to see them either in person or virtual. And if you wanted to do it virtually, like because like Miss Williams, she has like tutoring from 8 to 10 on Tuesday night. So she does that virtually from home after her kids go to bed. So it works out really well, but you can actually schedule a time. So you could schedule a time with her and she would get an email that you want to meet with her and then we can coordinate it. I'll do that too, like anytime. All I need is just a little bit of notice. As long as I'm home, I told you I try to check my email all the time. So I'm more than willing to either do you a tutorial or meet with you just to help you work through them. If that helps you kind of keep moving, then that's better for me. All right, so here's see the balancing equations and unit conversion worksheets and answer keys. So there's the answers. So if you do these balancing equation worksheets and you're like, I think I got them, you can check. Okay, so there's the keys right there. But the class that we had last week, here is the YouTube video for it. Okay, so that is the section 21. So that was from beginning to end what we did on Monday night. And then here is the marked up PowerPoint from Monday night. I'll actually take this down and re-upload what we've done tonight too. So if you want to go back and like look at what I wrote anytime, like something you're like, well, I think I wrote this, but maybe she wrote that. You can always go back and look at these. I'll just do this every single class. Okay, I just like put in the new marked up PowerPoints each time. And this all goes into the exam 1 module. Then once exam 1's done, then I just start putting them all in exam 2 so that you kind of got them. And if you want to go back and listen to them again, like kind of the stepwise processes, especially with the math. So the math review, that's one that's like significant figures, unit conversions, rounding, exponents. I did like another tutorial. So we haven't gotten through all of that yet, but if we get through that and you're like, that's a lot of math. Like there's a whole nother little review thing that I did with that. Okay?